Thanks for the introduction. I have put way too much stuff into my talk, so there may not be time for questions at the end, and I might even overrun, but we'll see how it goes. If you want to ask me questions, then just find me later and we'll have a chat. So usually I start with a slide that says my name and who I work for, but this time I want to, by way of introduction, I want to talk a little bit about my journey so far with Scala over the last few years. So along the bottom we have the time axis, and then on the left-hand side it's kind of unclear what this axis represents, but at the top we have like functional programming enlightenment. This is what we're all aiming towards. This is our goal. And then in the middle we have object-oriented development using Java and C# and languages like that. And at the bottom I've just put some languages that I don't like very much. So if you have any other languages that you dislike, just mentally add them down there. That's what we're trying to avoid. So I did a bit of functional programming at university. I did one course in standard ML, and I didn't really understand why we were doing it. It was a bit weird. Then I graduated and I became a Java developer. So I was doing that for a long time. And then about 2009, I think, I heard that Twitter were using Scala, and I thought, I want to be as cool as Twitter, so I'll try Scala as well. And I fell in love with the language. I started using Scala, but for a long time I was still using it in a very object-oriented way. It was kind of a better version of Java. Then at some point I rediscovered functional programming, and suddenly my path to enlightenment began. But it hasn't been an easy journey. Occasionally I discover some new horrible concept like comonads or something, and I just retreat. It's too scary, so I go back to my safe zone of object orientation, and then I'm kind of repeating that. So this talk will be partly kind of tips and guidelines that I've gradually learned over the last few years during this journey, how to write Scala in a functional or semi-functional way. And it'll be partly, at the end, I'll talk about a couple of things that I'm still kind of experimenting with. Like, I understand the concepts of these functional concepts, but I'm not quite sure how to get them into production code in a sensible way. So the talk will mostly take the form of case study of this app called Amigo that I wrote for work earlier this year. It's an AMI bakery. So the idea is that you can come along, it's like a web application, you can log into it, choose what you want to install onto your machine, like, for example, a Java runtime and Nginx and Node.js. You choose these, like, tick the boxes for what you want to install, you click a button and you can build an Amazon machine image, an AMI. It's implemented in Play and Scala. The domain of building machine images is obviously a very impure and very effect-heavy domain. So we've got like, we're building Ansible playbooks and Packer configurations, and that we're writing those to the file system, and then we're executing Packer as an external process. We're saving stuff to DynamoDB. So there's a lot of impure stuff going on here. And that's one reason why I decided to choose this app as my case study. It's not that it's a particularly amazing piece of code that I want to show off, it's just that it's quite a small, self-contained app, and it shows off quite a lot of interesting problems that you encounter in functional programming. It's event-driven, so when we run the Packer external process, we actually monitor the standard out of that process and parse the output, and based on that, we fire off events like a log message has been created or an AMI has been successfully created, and a lot of listeners on this event bus execute things based on these events. It also doesn't have many tests at the moment, which is something I'd like to remedy, and that's kind of another reason for this talk. The code it's open source, it's there if you want to follow along while we go through. I'll try to give you a demo very quickly. I'm tethering on my phone, so it might be a little bit flaky. Oh, it's quite small. So here's a chance to practice your Spanish. Everyone repeat after me. Hola, amigo. That's all the Spanish I know. That's it. So the idea, just to get you familiar with the domain and the terminology that we're going to be using here, the idea is that we have these base images. For example, there's one here for Ubuntu Xenial. So this is saying start with the official Ubuntu Xenial AMI, and then we're going to build stuff on top of that. We have a list of roles that have been created. These are implemented as Ansible roles. So you can choose what you want to install onto your AMI, for example, Java 8, Nginx, and so on. And then you combine a base image with some of these roles into a recipe. Here we have one that installs Java 8 and Nginx. You click the bake button. Hope this works. Yeah. So at that point, it has it's generated an Ansible playbook based on your roles that you chose. It's generated a Packer config file. It's spun up an external process to run Packer. And now it's just listening to the output from Packer and waiting for it to finish. And Packer has spun up an AMI, and it's going to run Ansible and install all of your stuff. So if we waited 10 minutes or so, then we would have an AMI at the end of this. Did that all make sense? That was quite fast. Okay, some nodding. So in terms of implementation, the package structure looks a bit like this. Some of this package structure is mandated by the Play framework. For example, controllers and models and views. Play makes you do that. But the others, I've tried to split it up by function, I suppose. So the Ansible package contains anything to do with Ansible and so on. So we're going to be talking first about what went well, or rather, looking through the source code of Amigo, what did I start to think was quite nice about Scala code that I write day to day. Not necessarily in Amigo itself, but mostly. And at the end, we'll have a quick look at ways that we could refactor Amigo to make it a little bit more functional, maybe. So we're going to be looking at these 5 things, but I'll just dive straight into functional modeling. So before we look at how we design and model things in a functional way, we'll just have a quick look at object-oriented style, just to compare the two. So if we were going to build this app in an object-oriented way, then it might look something like this, the UML diagram. So we might have a bake, which has a recipe, and a recipe has a base image and a role, and so on. So it's all composition. And you can see that in object-oriented design, the whole idea is to couple your data and your behavior together into one class. So a class has some data or some state, and it has behavior that it exposes. And the idea is that it encapsulates its state and exposes its behavior. So implementation in object-oriented style might look a little bit like this. We would have some traits for our recipes and all of our dependencies. They'd all be traits because we're good object-oriented programmers and we want to be able to mock them in our tests and so on. So we'd have a bake class which accepts these dependencies as constructor parameters, and then it would have an execute method which would call methods on its dependencies. So it's calling recipe.generatePackerConfig and so on. So that's pretty standard, I think, in object-oriented style. Nothing too exciting. So if we compare that with functional programming design, in FP we tend to decouple the data from the behavior. So we have data, which sits alone and it's just static and immutable, and then we have behavior, which takes data in and does something to it and returns new data. And they're completely decoupled and separate from each other. So let's have a look at the data side of things first. In general, in Scala and in most functional programming languages, you model your data using ADTs, algebraic data types. So an ADT is made up of sum types and product types, and we'll just go quickly through those. So a sum type is a choice or a union. It's like This thing could be an A or a B or a C or so on. It's when you have a choice of things. And it's represented or encoded in Scala using sealed traits or sealed abstract classes. So here we have the status of a particular bake, the bake status. So it might be running, it might be complete, or it might be failed. It's one of those. And then the other kind of algebraic data type is the product. So this is composition. It's saying this thing has an A and a B and a C. And this is represented in Scala using case classes. So here our bake class has all of these fields, recipe and build number and so on. And if you have just these two very simple concepts of sum type and product type, you can combine them in arbitrarily complex nested ways to model basically any data that you have, any domain, which is really nice. Now, Scala is obviously a strongly typed language. It has a useful static type system. So we want to use that to our advantage, use it as much as we can. So, for example, in Amigo, we have lots of different types of IDs, and they all happen to be strings. So AMIs have IDs, and recipes have IDs, and so on. And we don't want to get confused between these. If we were just passing strings all over the place, you could easily get your arguments the wrong way around, and just a very silly bug that could possibly take ages to debug, and it's just horrible. So the simplest way around that is just wrap everything in a case class. So we have case class AMI, case class base image ID, and so on. So not only do you get this safety where you can't accidentally pass the wrong type of ID to the wrong function, you also get more readable code. Like, you know that it's an AMI ID that you're passing around. You're using your domain language, your ubiquitous language, in your code. So your code looks easier to understand. Just an implementation detail here. This extends any vowel means that it's a value class, which is a feature of Scala that means that at runtime, or rather when your code gets compiled down to bytecode, all of this stuff gets erased, and so at the bytecode level, they are just plain strings. So you're not paying any runtime overhead here. You're just getting the benefits at compile time or in your IDE, but without paying the runtime cost. Here's a quick example of how this can help you using these wrappers around your IDs. So in the bakes object, we might have a function called update AMI ID, takes a bake ID and an AMI ID. And then we want to call that function down here, but we get the AMI ID and the bake ID the wrong way around. But the good news is we get a compile error here. We don't get a stupid bug and write the wrong thing to our database. Next up is errors. So a lot of people, when they first start doing kind of software modeling, domain modeling, they don't really think about the error cases. They're always interested in just the happy path, which is natural, I think. But really, any errors that you encounter are also part of your domain, and they should be modeled accordingly. So, sorry. So let's say, for example, we're trying to load an Ansible role from the hard disk. An Ansible role is just a directory full of files in a certain format. So a few things could go wrong here. The directory might not exist, or the files inside the directory might be just invalid in some way. So we're not going to throw exceptions. That's horrible. We could return a kind of nested either containing all of the different things that could go wrong. Also pretty nasty, because you'd have to do a kind of nested match on that. Not very nice. So one option is you can create an algebraic data type of all of the results that this function could return. So it might return a success, in which case it gives you the role that you wanted to load, or it might return each of these different kinds of failures. And then the return type of the function just becomes load role result. And you can do pattern matching on that, or whatever you like. The downside to this approach is that it's not monadic. It's just a class that like a custom class that you've created, so there's no monad for it. So you don't get things like map and flat map for free. So a slightly different way of doing it might be to only model the errors and then return an either. So you return an either of load roll error or the roll that you successfully retrieved. Now, if you've done object-oriented programming, you've probably encountered design patterns, the kind of famous gang of 4 patterns, decorator and flywheel and whatever. And in functional programming, there are similar patterns, things that people have discovered and you should know about and learn so that you don't keep reinventing other people's wheels. And the monoid is a good example of this. So let's say you have a result class which contains a count of the successes and failures of whatever processing you've done. We can implement a monoid for that class, which has an empty method and a combine method. So this says how do you create an empty result class and how do you combine 2 results into one bigger result. And once you've done this, if you're using a functional library like cats or Scala Z, then having this monoid available gives you lots of stuff for free. For example, there's a nice function called fold map. So for example, say we have a function that processes 1 page of items and it returns a result. So it returns a count of successes and failures. Oh, sorry, it's happened again. And then we have a list of pages that we want to process. And we can call fold map, pass in that function that processes 1 page, and that will take care of all of the kind of the boilerplatey plumbing of mapping the function over all of the pages and then combining the result together for you, all in 1 line. So that's quite nice. And there's plenty of other examples of things that you get for free if you have the monoid for your model classes. So that is data. In summary, use algebraic data types, use the type system as much as you can, and just model everything that you can think of. So we're going to look at behavior, which is comparatively simple, really. So behavior is just plain old Scala functions. It's just objects containing functions. This is generating an Ansible playbook. So we have one function that takes an Ansible role and turns it into a string, and then we have a bigger function that uses the smaller function by calling it, obviously. So in general, we have this kind of hierarchy of functions where we have small functions building up into bigger functions. I mean, it's so obvious I don't even need to say this. But the only thing is that some functions are pure and some are not. So this is a slightly more complex example. This is what we want to do when we want to create an image given a bake model. So we're creating a machine image here. So first step, we're going to generate the playbook, the Ansible playbook for this configuration. That's pure. That's just taking one of our model classes and turning everything into a string. But then, next step, we have to write that to a file. Obviously, that's impure. Next step, we do the same thing, basically, for the Packer configuration. So we generate a string, that's pure, but then we write it to a file, impure. And then we do probably the least pure thing you could ever do, which is executing an external process. So when you're writing functional code, you need to bear in mind which parts of your code base are pure and which are not. And obviously, we want to make the pure functions box as big as we can and the effects box, or the impure part of our code, as small as we can. This is what people talk about when they talk about a functional core and effects at the edge. So we're going to look at ways that we could do that, potentially. Next, prefer objects to classes. So what I'm talking about is here, do we have an object called Packer runner, which has no constructor parameters because it's an object, and it takes a bake in as a method parameter, or do we have classes which take the bake as constructor parameters. And my claim is that I prefer to use objects, the top version. Why? Basically because they are simpler. They're the dumbest thing that you have available in Scala. They have no life cycle, they're just always present, so you don't need to worry about whether you're leaking them or have they been instantiated properly or not. And it's, yeah, I suppose it's the principle of least power. It's just a big bag of functions. It's the simplest thing you can use to get the job done. So there are some downsides compared to classes. For a start, there's no constructor anymore. There's no convenient constructor where you can pass in a bunch of stuff to your class before calling a method. So you end up passing a lot of parameters around. You need to pass everything into every method. And there's a few solutions to that. A kind of slightly hacky partial solution is to just make lots of them implicit so you can't see that you're passing them around. And if even that gets a bit crazy, then you can bundle them up into kind of wrapper classes that contain a few parameters, that kind of smaller number of bundles. So this is an example of where I do that in Amigo. So we have the recipes object. This is a data access object for looking up recipes in DynamoDB and writing them to the database. So we have a def list, which gets us a list of all the recipes, and that takes a Dynamo as an implicit. And then in the play controller, where we're calling that function, recipes.list, we don't see that we're passing the Dynamo into that object. So we don't clutter up our call site with all of our implicits. So it's not perfect, but it's a reasonable solution. One caveat, Daniel Spiewak, whose opinion I respect, says this is an anti-pattern and you shouldn't do it. And his reason is that this can lead to resource leaks. If you are passing resources like DB connections and things as implicit, then it's easy to leak them and not clean them up properly. But in my defense, I think if the resource lifecycle is the same as your application's lifecycle, for example, in my case it was a Dynamo client, a database client, which you never need to actually manage as a resource, then this works. It's fine. Next problem, how do you do dependency injection? If you do object-oriented programming, then it's pretty standard these days to do dependency injection and inject your dependencies into your classes. So I'm going to answer that with a question saying, why do we want to do dependency injection? I think there's two slightly different reasons. One is that we want to mock our dependencies so that we can test our piece of code, our unit of code in isolation, write a unit test, and mock out all of its dependencies. And the other one is to separate our interesting business logic from the nuts and bolts of managing resources like database connections and things. So in object-oriented land, we tend to think of classes as being dependencies, and we build up this kind of mental graph of dependencies. So this class depends on these two, and this one depends on these two, and so on. In functional programming, it's slightly different mindset. It's more about kind of functions, bigger functions being made up of smaller functions, which are made up of smaller functions. So it's a kind of a Russian doll of functions. But if you think about it, these are also dependencies, really. There's no way to test the big function in isolation from the smaller functions that it's calling. So if we want to do that, we need to pass those functions in as parameters to the function. So this is a slight rearrangement of the code that we had before. This is creating an image, a machine image. But this time we are passing in all of the functions that it calls down here. We're passing them in as parameters here, so that in our tests we would be able to pass in mock or dummy versions of those and test that the function is calling them as we expect. It has cluttered up our method signature quite a lot. We'll look at ways that we can alleviate that a bit later. So the second reason was resource management. So say we have some operation that requires a DB connection. So probably the worst thing that you could do is create a new DB connection and then close it again once you've finished using it, all inside the method. That would be incredibly difficult to test, and it's obviously a massive side effect. Slightly better would be to have the DB connection passed into the method, so that the person calling your function now takes responsibility for creating the DB connection and cleaning it up afterwards. But we can do even better. We can do what is known as currying. So what's happened here is that instead of passing the DB connection in as a second argument, we've passed it in as a whole new argument list. And the way that this works, or the reason that this is useful, is that you can now partially apply this function. You can call GetItem, pass in the ID that you want, 1, 2, 3, and that doesn't actually do anything at that point. It doesn't get anything from the database. All it does is return another function that says, if you gave me a DB connection, then I would do this to actually get it from the DB. So this function has now suddenly become pure, and purity is something that we like. And it's kind of a very small, a simple example of what is kind of a main tenet of functional programming, which is separating description from execution, or deferring execution for as long as we can. So we're building up a description of what our program is going to do at some point in the future, and then when we're ready, on the edge of our program, we can call run, we can pass in the DB connection, and all of that impure stuff will actually happen. This is called currying. It's named after this guy, Haskell Curry, whose room we are in right now. And it's another nice feature of it, which we will come back to, is that it makes these functions composable. So if you have a lot of these functions which all take a DB connection and return something, then you can compose them together into another bigger function which, again, will take a DB connection and return a result. I'm going to skip very quickly through the next couple because they're not quite as interesting. Avoid traits. I tend not to use traits very much these days. They're quite attractive when you first come from object-oriented programming background, because you're very used to using interfaces in Java and C++, C# or whatever. So they can be used like that, which feels very natural. They support fancy things in Scala, like you can use abstract override to create decorators and things. You can get quite clever with them. But they are quite confusing, I find, especially if they're overused. If you have a massive hierarchy of traits all overriding each other and inheriting from each other, it can get really complicated. It's hard to find where the actual implementation is that you're using. There's horrible things with initialization order where you can actually end up with null pointer exceptions, which is something you're not supposed to see in Scala ever. And in general, it kind of encourages this object-oriented mindset where you're doing overriding and inheritance and so on. And that's something I want to get away from and don't want to encourage myself into. So a corollary to this is that you can't use the cake pattern, but that's fine. Don't do it anyway. Similarly, don't use lazy vowels. So lazy vowels are lazily initialized vowels, obviously. They have a runtime overhead, but more importantly, they have a kind of a cognitive overhead for the programmer who's reading your code, or who wants to write something that calls your function. Because the initialization of this lazy vowel might be really expensive, so it's kind of similar to a side effect, but it's kind of hidden. It's a sort of implicit side effect. So I find them quite confusing, and they're often used by people who don't quite understand them. They've just put the word lazy in for no good reason. So if in doubt, don't use a lazy vowel. Just finally, what Amigo got right. minimizing boilerplate. So boilerplate is something that I really don't like. I'm quite lazy and I don't want to just write out very boring code over and over again. So I'm always on the lookout for ways techniques and libraries to avoid doing that. So this is what the real world looks like. You have your data and your behavior, but then you also have a whole bunch of glue and wires and boilerplate and JSON encoders and play framework stuff and all of that, which is something we want to minimize. We want to make that layer as thin as possible. So just a few examples of libraries that I use in Amigo to avoid that. The first is called ScamMo. This is a DynamoDB access library for Scala. And it's under the hood, it uses shapeless to automatically derive formats for all of your case classes. So given any case class, it can automatically work out how to write that to a Dynamo table and how to read it. So you don't need to define any kind of format or codec. The next is called AutoMagic. This is a library that I wrote myself. It uses a macro to transform between very similar model classes. So say I have a domain level model of a bake I'm using here. And I want to transform between that and my DB model of a bake, which are very similar, but subtly different. Because, well, the DB model contains DynamoDB specific stuff. And I don't want that leaking into my domain model. So I have separate models, but I want to transform between them with no boilerplate. And that's what this library allows me to do. And just a final example, there's a library called enumeratem, which again uses macros under the hood. This is a way of taking your sealed trait hierarchies and making them look like Scala or Java enumerations. So you can look them up by name, like the example at the bottom. So it's a very small thing, but again, I don't want to be writing that boilerplate and maintaining that boilerplate whenever I add a new entry into this list of values. Okay, so that was just me bragging about Amigo for half an hour. Now I'm going to talk about some things that I don't like about the code that could be improved. I'd like it if there was a better separation of the pure and the impure parts of the code. For example, you saw that it was generating an Ansible playbook, but then writing it to a file, all in the same 2 lines of code. It would be nice if we could avoid that. So I did a kind of experimental refactoring to use the reader monad to avoid that. And then you can take things even further than that. You can separate description from execution for your entire program by using what's known as the free monad. So you create an algebra of all of the operations that your program is going to do. And so your program becomes a description of a list of operations in this algebra. And then as a separate step, once you've generated this description, you can then run it using an interpreter, which will actually do all of the impure stuff, like writing to the database and so on. Unfortunately, there's no way I could fit all of this into 45 minutes, so the free monad stuff will have to wait for another talk. We're just going to look at the reader monad today. So what am I looking to achieve here? Ideally, by separating the impure from the pure stuff, I'm going to make the pure code more testable, so I can write tests to cover more of my code base. But at the same time, I don't want to lose much readability or understandability. So if I end up having my code full of type lambdas and all kinds of crazy syntax and quite abstract functional concepts, then maybe it's not worth the trade-off. And when you think about this trade-off, you need to think about who is the target audience. So, for example, if you're working in a team of developers and maybe some members of your team are not as comfortable with functional programming, or they're just getting started with Scala, then maybe you don't want to bamboozle them with very clever code that does really complex functional stuff. So, We're going to have a look at whether we can refactor Amigo to use this reader monad for dependency injection, and hopefully that will make things a bit more testable. So the reader monad is a monad that wraps a function f from a to b. So it's just a very simple example. Say we have a function f which goes from int to string. We can wrap that in reader. I'm using the cats library here, the cats reader. And that wraps the function, and then if we want to actually run it, then we can call the run function, pass in an argument, and it gives us a result. So why on earth would we want to do that? Let's have a look. So if we just have another look at the currying that we were looking at before, this is exactly the same code that we saw a few slides ago. So this is our GetItem function, which, given an ID, it returns us another function, which, given a connection, will actually do the operation and get the item from the database. So let's have a look at how that function works when we need to combine it with some other functions to make a bigger operation. So we've got the same function up at the top there, getItem, which reads from the database. We've got another function quite similar, which it takes an item and a new name for that item, and it renames it and writes that to the database. And then we've got a function down here which combines these two. So given an ID and a new name, it will look up the item in the database and rename it. So it's calling these two functions here. And you can see that because we're doing this currying, we need to pass this database connection around a little bit. We get it passed in here, and then we need to pass it individually to each function that we're calling. And the reader monad gives us a little bit of help there. It makes that a little bit tidier. So if we look at the same code but now using the reader monad, so we're wrapping everything in reader. So our getItem function up at the top, that is now a reader, and it goes from DB connection to item. We've got our rename item, which again we've turned into a reader, and then we've got our third function which composes them. And now, because we're using the reader monad, we can compose them in a nice monadic way. We can write everything as a for comprehension, and we love for comprehensions. And you can see that we're not passing explicitly the DB connection around. It's just the monad is taking care of that for us, that kind of plumbing. But apart from that, it looks very similar to the code that we had before. Let's look at a slightly more realistic example. So when we get an item from our database, we pass in an ID, but we can't just assume that that is actually that in the database. It might not be there. So we need to return an option of item. And let's see how that looks in the reader monad version. So suddenly, to deal with this option, things have got slightly more complex. We're now using this slightly more generalized version of reader monad, which is called reader t. So this wraps a function that goes from a to f of b. So it's like, for example, DB connection to option of item. I don't know why they put the 3 type arguments in that order. It seems quite strange to me, but never mind. So now that we've got this reader t, we've got our first function returning a reader t, but the second one is still returning a reader. So now our types don't line up properly, and we need to slightly massage things to get them both into a reader t option DB connection item. And the way that we do that is with this lift method, which is underlined at the bottom. So there's a few helper methods like this lift, just to get all of the types to line up. So how would all of this look in Amigo? So this is the starting point. This is more complicated than all of the code I've shown you so far, but this is quite close to the real code in Amigo. So I'll just go through this line by line. This is the function to create a machine image. So we pass in a bake, we pass in Prism, which is a Guardian-specific thing that looks up all of our AWS account numbers. So it's a web service, so this will make an HTTP call to an API and get the the AWS account numbers back. We pass in the event bus that we will need to send events to once we've started listening to our Packer process. We pass in some Packer configuration. We generate a playbook YAML from the recipe. We write that to a temp file. Then we make our call to that API to go and get our AWS account numbers. That returns us a future. So we flat map over that future. We build the Packer config, write that to a file, and then we're finally ready to actually execute Packer. And we pass in all of the stuff that we've done, like our playbook file and our Packer config file, and we're done. And this thing will return us a future of the exit code of the Packer process. So if it was a 0, then everything went fine. If it was a 1, then Packer failed for some reason. So we're going to try and readerify this step by step. So step 1, we're going to pass some of our functions as arguments. So rather than hard coding all of the functions that we want to call, we pass them in as arguments. And that means we can pass in mock versions of those in a test if we want to, for example. So our type signature is getting pretty crazy at this point, but we've got a bunch of functions at the top that we want to pass in as arguments, and then we've got the actual arguments that we want to pass, and then the rest is the same. We're just using the arguments, using the functions that were passed in. The next step, we can tidy this up slightly by using currying to hide all of that wiring, all of those functions that we need to pass in. We can do that in one place, in this file called app components, which is where I already have a lot of kind of wiring and boilerplate stuff to kind of build the components of my Play application. So in there, we can hide away a bit of this wiring, and then we pass into the controller just a function that takes, or the partially applied function that takes the bake, the event bus, and so on. So we've reduced the amount of stuff that we need to expose to the Play controller, at least. We've hidden some of this wiring away. Next step, we bundle all of our resources and dependencies and things into a context object. So we've got a create image context, which has the event bus, the web client, the Packer config, and so on. That's just a slight refactoring. Now, once we've got this context object, we can readerify everything. So now we've created a reader, a reader T rather, which takes a create image context and returns a future of the exit code of the Packer process. So we've turned the create image method into a reader, and we've also turned anything else that we can into a reader, or a reader T. Anything that's using any of the dependencies in that context, we turn it into a reader T. And finally, once we've done all of that, we can compose everything into a nice for comprehension, because everything is now a reader T, and we can just list the steps that we need to do in a for comprehension. Which looks quite nice, but that's not quite the end of the story, because actually the functions, or the arguments that we were passing in here, some of them were reader T's, some were just plain old functions, some were readers. So they're all slightly different shapes and different types, and we need to massage them all into reader T, create image context, future something. So in this ellipsis section here, there's actually a bunch of horrible code that looks like this, where we have to just transform everything from one type into the right type. And this can get pretty painful. I've made a little cheat sheet here. This is what you need to do. So if you want a reader T of F input and output, but you have one of these, you need to call that. If you have one of these, you need to call that, and so on. So after all of that, I can now write a test for my create image function. But it is quite cumbersome, and it's not really a very useful test, to be honest. It's quite a hollow test, because we've removed all of the interesting stuff. and we've injected them as dependencies. So the thing that we're left with, the thing we're testing, is not actually doing anything useful. It's just a very simple for comprehension. So we can test that it runs things in the right order, but really it compiles, so the type system has already told us pretty much everything useful about it. And probably a 2-minute code review could do the job of this test. So, slightly disappointing conclusion. But to be fair, this was not really a very good use case for reader, I don't think. The reason is that all of the dependencies that we had, those were all dependencies that had the same life cycle as the application. They didn't have any kind of resource management that needed to be done, like creating them and tearing them down. So they could have just been injected all at the time that we built the application using plain old currying. In the real world, as you saw, using this lift and pure and local boilerplatey stuff to wire things into the right, massage things into the right type is quite painful. And finally, if you do want to use the reader monad, I would probably start with it. Don't try to refactor into it retroactively. Just very quickly, if you've ever seen the word Kleisli and you're wondering what it means, now you know, because reader T is Kleisli. They're exactly the same. They're just different names for each other. And reader is just a special case of reader T. So it's a special case of Kleisli. Free monad, as I said, sorry, I've run out of time. That'll have to wait for another talk. So in summary, model your domain functionally. Try to minimize boilerplate as much as you can. And defer execution for as long as you can. So separate description from execution. But there's more than one way that you can do that. In this case, for this particular use case, the reader monad was not the right way to do it, but it was fun trying it. I've put a few useful links up here. So I'll put the slides up online and you can have a look at these, but that's all I have for you.